All right, good morning. This is Tim Stewart. I'm president at Visual Decisions, and we're here today to talk about root cause analysis and how there's been a revolution over the past 5 or so years in how to actually do that. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve continuous improvement since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. Our customers have seen dramatic improvements such as a 30% increase in OEE, 50% scrap reductions, and much more. All right, so let's get to it. Just as a quick procedural note, if you have questions during the presentation, please enter them into the Q&A, and I will get to them at the end of the webinar. The agenda today is pretty straightforward. We're going to take a look at root cause analysis and how Industry 4.0 solutions can really help change the way that you think about it in the first place, but then also perform root cause analysis, and to some extent can even automate it with those solutions. So to get started, looking at what root cause analysis actually is, in Toyota way, Jeffrey Liker, lays out kind of the Toyota 7-step practical problem solving process, where initially you're defining what the problem is. You clarify that, you locate the area or the point of cause, you go through your 5 why analysis, and then you put in countermeasures, you evaluate how well those countermeasures work, and then you standardize that across the process. And root cause analysis itself is kind of the center part right here, where at Toyota they've standardized on the 5 why problem solving or root cause analysis process. There's a number of different ways to go about that, and we'll talk about a number of those here. But what I wanted to spend a little time on up front is how Industry 4.0 will not only help with the root cause analysis process itself, but defining the problem in the first place. And very often, getting the problem defined correctly is actually the most important part of the problem solving process. If you define the problem incorrectly to begin with, you're not going to achieve the solution that you're hoping for. And so by having that very rich data in the first place that tells you exactly what the problem is, what's going on within the process, you'll be much more successful in actually performing that root cause analysis and putting solutions in place. So just wanted to cover that up front. But as we look at the root cause analysis process itself, there's a lot of different ways to go about that. 5 why is one of those. But when we were kids, we were taught to look at who, what, when, where, why, how, and then we can look at Fishbone diagrams, FMEAs, graphical evaluation, statistical analysis of factors, things like ANOVAs, analysis of variance, design of experiments, etc. And so if we kind of start with the simple ones here. As we're looking at a problem and we're trying to determine what the cause is, it actually is good to start with the basics. Does the problem actually change when is it influenced by who's running the process? So if I have different operators that run that process, does the problem only show up when one of the particular operators is doing that? Maybe it's a training issue and they're just not running the process correctly. Or maybe it's something that only happens at particular times. When we start the process up on Monday morning, we see a lot of problems. So actually looking at these different factors is very important to getting the problem analyzed and fixed correctly. And as we look at how Industry 4.0 can play into this, as we're collecting information from the process, whether that's machine data, quality data, whatever it might be, we want to make sure that we contextualize that information. So collect who's running the process, what part is being run, everything about, that process as it's occurring. We want to be collecting that information in real time. And what that's going to help us do is to identify all of those, 5 Ws and 1H for when we do have a problem, whether it's looking at the machine going down, whether it's quality issues, whatever it might be. We have that contextual data to be able to answer these questions about the 5 Ws and the H. Rather than trying to collect that information by hand, if we have that data collection going 24/7, 365 days a year, then we're very likely to be able to look over time and be able to pick up on, does the process behave differently depending on the operator, depending on what time of the week. Maybe it's something that happens right after lunch. Might be that quality issues kind of get past the operators, after they've been staring at the process for 3 hours in the day and so forth. And so there are a lot of different things that if we collect that information and analyze that with that full context, that it really, really helps us understand what's actually driving the problems in the process. I don't want to ignore 5Y. It is a very, very good problem-solving process or root cause analysis process. And the idea here is that if you're not familiar with 5Ys, what you're trying to do is to kind of break the problem down. You are looking for, okay, what is that proximate cause? What is the thing that causes the machine to fail? But then you're not satisfied with just understanding that proximate cause. What is it, the thing that causes that issue to occur? And then you keep regressing down further until you actually get to the root cause of the problem. And one trap that some people fall into as they go through this analysis is, basically only going down one path. They say, okay, what are the different reasons why this fails? Well, this is it. And then what are the different causes for that? Well, there's this one cause. And then what causes that? Well, then, et cetera, going down one single path. Whereas really what you need to do is to look at multiple reasons at each level for why that's occurring. And what you end up with is more of a tree structure for, what are the different reasons why it can fail, and then what are the different causes for that. And then, for each one of these different branches, you end up with different weights that different probabilities of that cause of failure. And so the Fishbone or Ishikawa diagram is really just a 5Y type of analysis, but going through it in a much more rigor and looking at multiple reasons why it fails. And the other nice thing about the Ishikawa diagram is that it reminds you to look across different causes for, what are the influences of people in that process, the machine itself, the material, the method, management, environment, et cetera. And what are the different contributing factors, from each one of those different areas into that problem. Now, for both 5Y and for the Fishbone diagram, we can look at how these solutions can help you with that analysis as well. So at a bread manufacturer, as we implemented systems to collect information for both downtime and for quality issues, but focusing on the downtime example for now, as each failure occurred, what we had the operators do was to collect information about, was it an equipment failure, was it process failure, et cetera. And then if it was an equipment failure, which piece of equipment was it that failed? Within that, what was the top level cause? And then was there another level of cause that they could assign to that after that? As well as capturing contextual information about who was running the process, what product number was being run, et cetera. And so then as we capture that information and went to analyze it, what we could do is we could say, okay, the biggest loss over time is this equipment loss. So if we click on that, then start to just drill down into those issues, what we could find is that the biggest source of equipment loss was in the oven. And then within the oven, what we were seeing was that we were getting these big spikes that were occurring periodically. And that trend of time loss also helps you with the analysis. Looking at how these failures are occurring, most days we had very, very little time loss in the oven or due to the oven. But then we had the big spikes. So what that tells you is that it's not kind of an error proofing or Poka-yoke type of a solution that you're going to need. It's not something that's occurring frequently. It's something that just you have those big spikes. It's something that you have a periodic failure. And so for this, it's much more of a preventive maintenance type of a fix normally. And so in these situations, what we were looking at was capturing the additional detail about what it was within the oven that was failing. And so we got the operators to go to that next level and assign that next level cause. And what we found was that the oven shelves were flipping due to broken pins. And what was happening is, as the conveyor was cycling in and out of the oven, the pins were fatiguing over time. And eventually those pins would fail, the oven shelf would flip, and we would have to shut the whole process down and clean it out, restart it, etc. And so whenever the failure occurred, it led to a very big loss of time because we had to cool the oven down in order to fix the problem. And so simply by identifying this, putting a preventive maintenance program in place for those pins to replace them on a periodic basis, we were able to eliminate the single biggest cause of downtime in the plant very easily because we had done that proper root cause analysis, captured that information. Graphical analysis is another way to go about this. In addition to what I just showed, there are a lot of different types of charting that you can do in order to analyze a process and really get at the nature of the problem. So as an example here, we captured information for a company that did power generation. And the red line up top represents the set point for the furnace and how that was moving over time. And then the blue dots were the actuals. And where we had variance between the blue dots and the red line, the company called those dents in performance. And so then the line down here represents the size of the dent at any given time. And so the run chart here was one way of looking at, over time, was there kind of a pattern to when these were occurring? Another look that we took at this was analyzing this by set point and then by the size of the dent. Was there something that we could look at that would tell us, was the size of the dent correlated to different set points, or was the problem happening at particular set points? And what we were able to identify was that if you look at this curve, there are really three big set points where this is occurring, and then kind of a fourth one where it's also fairly frequent. But we worked with engineering to identify, what was it about those particular set points that was causing issues? And then we further did this where we looked at different dimensions of the information that we're collecting and the size of the dent and so forth, and looked for correlations between the size of the dent and different factors that were driving this, and so that we could identify correlations in that data. And then we actually also ran the numbers to get what the size of the correlation was. And being able to perform this kind of graphical analysis, our eyes are wonderful tools at picking up information from that data that tell us how to really track that down and hone in on what are the different things that are influencing the performance of the process. Another problem solving or root cause analysis method that is commonly done is a failure mode and effect analysis, an FMEA. And when we're looking at process FMEAs or product FMEAs for quality, the typical process for doing this is to kind of lock a whole group of people, a cross-functional team, into a conference room and have them basically brainstorm what is every potential failure mode and cause or mechanism of that failure. And then basically take a swag at what the severity, what the probability of occurrence is, and what the probability of detection is. And then multiplying those three numbers together to get your risk priority number, and then brainstorming recommended actions and so forth for those. And that's, the traditional way of going about this. But if you're capturing that information on a 24/7 basis, and you're going through and you're assigning causes to those failures and so forth, if you've done an FMEA already, you can actually utilize these failure modes and causes of failure as your failure tree that you're capturing that information against, rather than just setting up downtime reasons within the process or within the software and having that completely dissociated from the FMEA analysis that you've performed. You can actually link those together and utilize those FMEA root causes as the things that you capture information against. Just train your operators to look for those different things. And so then as you're capturing that data, you can actually kind of automatically assign, what, when those failures occur, get that tied into what you have on your different failure modes. And now as you look at those Pareto diagrams of the different failures over time, you can automatically assign what is the probability of occurrence. You can automatically assign the severity from how much downtime you're seeing and so forth. And also, if you think about the probability of detection, when you're thinking about what data you need to collect from the process in the first place, you should utilize that probability of detection to think through what is the information I have to collect from the process in order to be able to find this particular instance of this failure mode. And then we can start to tie that into some of the more advanced systems that we'll talk about in a few minutes to automatically classify these different failure modes and tie that into the FMEA analysis as well. And then kind of the last method of doing the root cause analysis that we'll talk about today, from a statistical analysis of factors, being able to run ANOVAs or DOEs or anything else, having that information of the detailed information, the detailed data from the process, as well as the output variable of whether it's downtime or quality issues or whatever it might be, actually allows us to run a historical design of experiments. So if we have that detailed information, we have the different factors and signals for those factors being collected, and then we have the outputs, what we can actually do is run a design of experiments, but instead of doing it forward and having to spend the time it takes to collect that information with enough data to have enough instances of that particular failure mode, if we have that information historically, we can use the last 3 months of data, run that design of experiments, and actually look at all of the different factors and come up with our correlations and our factors and everything else to be able to determine, what are the most critical factors that drive this particular behavior. And so that can save us a tremendous amount of time if we're able to do that off of the historical data and then utilize that hypothesis for testing going forward. And so very powerful to be able to run these tests and so forth based on the history instead of just having to do it going forward. So I alluded to this a little bit in terms of being able to utilize artificial intelligence and machine learning to automate this analysis. and being able to kind of do this in real time. And so the idea here is that instead of having our operators um, having to go in there and assign what is the failure mode and so forth that has actually occurred, or basing that on the machine telling us what is the fault code that occurred, and utilizing that to assign the reason codes and so forth. Can we actually utilize machine learning to do that for us? And these systems are very, very good at being able to run what we call a classifier system. And what a classifier system does is it groups data into different classifications. And it takes those different signals that we're seeing from the machine across many different tags or many different signals, variables, et cetera. And we'll utilize those to kind of group the different problems that we're seeing. And so if you think back to when we were talking about the FMEAs and the probability detection, and I talked about being able to tie the different signals that we're trying to collect from the machine to those different failure modes, the goal here is to be able to identify, what are those signals that are going to be able to tell us when a particular failure mode is occurring. And if we can do that, then we can automatically classify, each instance of downtime or each instance of, a quality issue to the different causes that we have. And then if we find something new that we're not able to automatically classify, then we can get the humans involved to go through and perform that root cause analysis for what was the cause for this particular instance of downtime. And then we can go through the standard process and add to that model. But being able to do this automatically really frees up our labor to shift the focus from doing the analysis of what happened and that kind of post-mortem to shifting the analysis to what do we need to do to prevent this in the future. And so from the utilization of our people and the time in the process and so forth, we can eliminate what is essentially waste in terms of doing the root cause analysis and shift that focus to having them actually improve the process and put the POCIO, put the error proofing in place, put those more preventative measures in place, make sure that we have the pins changed out on the conveyor belt more frequently and so forth. And so if we look at an overall framework for analyzing the problems and putting the fixes in place and so forth, if we look at this from a couple of different perspectives, both from a real-time perspective of as things are happening, what can we automate to what can be done by the worker at the line in kind of near real time, or something that's done away from the process but still somewhat real time, all the way to what are we doing on a weekly or a periodic basis to analyze what are the biggest failures that we're still seeing, doing that Pareto chart. And outside of firefighting mode, looking more at a preventative mode of let's tackle what is our biggest source of downtime, what is our biggest source of quality misses and so forth. And each one of those can be aided by this analysis, by what we're doing from a root cause perspective of whether it's collecting the data and being able to inform our manual process of doing the root cause analysis, as we saw with the bread manufacturer, or whether it's putting those classifier systems in place and automatically performing that root cause analysis, as we're doing with other customers. Each one of those allows us to have that focus really being on, instead of monitoring and detecting the problem or understanding and diagnosing the problem, now the focus really shifts to deciding what we need to do and then taking actions. So that's the second axis here, moving from monitor and detect all the way down to act. And so, looking at some lessons learned from working on this with other customers, one question that we get is, what is the right time to start collecting the data? And it's kind of the same answer as, what is the best time to plant a tree, 20 years ago, so that you have a nice fully grown tree. The best time to start collecting data isn't when you're trying to do the analysis. The best time to start collecting data is, last year or the year before, so that you have that historical information that you could run those historical design of experiments or ANOVAs or anything else. The second best time to plant the tree is right now, so that as problems come up in the future, you have that data going forward. And so, the best time to take action is in the past. The second best time is do it now. The next question is, what data should be gathered? And it's a good question because, if we look at this historically, it was expensive to collect this information. The good news is that with IoT systems and the cheaper cost of sensors and data collection, data storage these days, it's a lot cheaper to do this than it was in the past. And so, if you have, if you're trying to decide where you should capture data and looking at prioritizing things, certainly if you have processes that are out of control or critical processes within your operations, start collecting all the data you can from those processes right away. But you can also look at, if you've done like an FMEA across your different processes, then you can start collecting data where that FMEA tells you that data collection is critical. And you can start to analyze, where do I have severe issues, or where do I think I have severe issues? Where do I think I have high probabilities of errors, where I don't have good probability of detection today? And those are the places that are going to be highly critical of being able to go in there, collect additional data, collect additional information, and being able to automate detecting some of those critical errors. So the next piece is data cleansing and avoiding garbage in and garbage out. One of the questions that I very commonly get is about manual data collection versus automated data collection. And there's really not a right or wrong answer here. As much of the data that you can collect automatically, obviously it's good to do so, but machines aren't necessarily good at knowing, the fault codes that you're getting from machines are really the symptom of what's happening as opposed to the root cause. So you need to collect those process variables, what's happening in the machine during the process, whether that's pressures or temperatures or vibration or noise or anything along those lines. And then you also need to be able to collect the data as the process is occurring. But you still may need to get information from your people. And just an example there is, when you have an e-stop, e-stop as a fault code doesn't tell you much. And you may not see anything in those process variables that tell you why the e-stop occurred. And so you still need to collect some information from the operator for that higher level, that macro perspective, that human perspective of what is driving that downtime, what is driving those quality issues within the process. And the other aspect there is that there are things like breaks, lunches, et cetera, that are human driven. It's process driven for why the process is stopping. And it's good to have information about those sources of downtime as well, because you have to be able to account for those things, and you may have an opportunity to remove downtime from the process by kind of overlapping, when people get breaks and lunches and so forth, doing other things within the process in order to eliminate those sources of downtime as well. And so it is very important to have data analysis in place and using that information, having the operators see that you're using that information, and not beat them up for it, but incorporate them into the process of, now how do we take this information and actually make the process better? How do we make the operator's life easier? And if you involve them, and if you have that focus on the process improvement as opposed to using it as a bludgeon, then usually you can get pretty good data from the people involved in the process as well. So with that, I want to thank everybody. If you have questions on this process, please reach out to me, tim@visualdecisions.com, 630-957-8096. And I look forward to hearing from everybody on how you can apply this within your business and how it might be able to help you. And also, happy holidays, happy New Year. And we will have another webinar next Wednesday that kind of takes a look at all 40 webinars that we've done this year, and hits kind of the highlights from each one of those. So look for that. And other than that, we'll start everything up again after the first of the year. Thank you. Bye-bye.